All right, so let's start with that. Okay, so I just want to explain the setup. So we probably talk a lot about the different parts of the Era infrastructure and the stuff. So what we have here, I can, as you may see, where can I see it? Right, so essentially this is end-to-end video streaming. And as you can see, we have the little drone on the bottom left of this diagram. That's right. Right, so here is a drone, and so here is our egg farm base station, and has many different type of access radio networks. So the drone will talk to our Ericsson base station. So then from that egg farm base station, we will go through our Era Hall, essentially wireless backhaul, and to reach the Wilson Hall base station. And so then from the Wilson Hall base station, we can reach the internet via two different options. So we can either go through the fiber or campus network, right? So that's the kind of traditional way of reaching the internet. Or we have this huge basic satellite communication channel. We can go through that as well. So that's very interesting. Essentially, we have this essentially three different type of wireless links, wireless hops, right? So end to end. So what we're going to show is what the drone will fly in the field, looking at the corns and crops and so on. So that will eventually send over to the YouTube server, and you can view that video from anywhere you want in the world, right? So that's basic end-to-end video streaming type of demo. Okay. So I will explain a little bit more and each step in more detail, and so the setup. So then Owen probably will show the interface and so video streaming part. Okay. So again, from the drone, so this is what we have. Aurelia X8 Max drone. So that's a fairly large drone and can carry up to 20 pounds of payload. So that's what we put in there with our Quacktail RG530F radio. So that's a special type of radio, can work with Ericsson base station in SA mode. So it's very unique type of user equipment radio. So then with a small Intel NUC computer and to connect the Quacktail radio and with IP camera. So that's essentially set up with that drone. You can see the drone is sitting there right now. So in a cornfield, and so well, actually that's soybean. Okay, it's not corn. Soybean field is a little bit shorter. And so under the drone, so there's a small car that's carry basically all the different components. Okay, so that's the drone. Drone will fly and talk to the base station. So that's the tower. That's the egg farm base station. That's where we're going. All be there after the demo session, field trip. We're going to see that tower in person, right? So that one has all kinds of different antennas and some point-to-point link as well, right? So that's the one there. Then so that's the one particular one. So we're going to use the Ericsson base station, right? So we have both mid-band and millimeter wave band support, okay? So then from that, so then we're going through this Era Hall link to reach Wilson Hall base station, right? So the Era Hall part is basically, that one has three different types of links, the microwave and a millimeter wave link that we are using, Aviat WTM radios, and so also we have our own Era optical FSOC link as well, so that one, and also between the two base stations, okay, from the pole and to the rooftop, okay. So then from there, the Wilson Hall base station, so probably you can still see, and so that's the on the top right picture, right? So that's to show the entire Wilson Hall rooftop setup with the cabinet where we have our edge servers, and we have the radios and antennas behind the edge server on the penthouse, right? That's a whole basic rooftop configuration. It's quite a busy base station to have this many different capabilities. Okay, so then once the video stream reaches the edge server, so then that will actually go through the Hughes OneWeb satellite terminal. So thanks to Hughes' generous donations, we have this one set up and ready to serve as the backhaul as well, right? So that's basically sit right next to all the other equipment on the Wilson Hall rooftop. Okay, and then finally, through that link and then go through the Hughes network, eventually to reach the YouTube and or any public IP server. Okay, so that's basically the entire setup and with some technical details and model number and so on and so forth. Okay, so that's what we have here. Okay, and so then as far as the drone flight trajectory, this is how it look like. Again, so that gold star, that's our egg farm base station, and so then there's all the cornfields and soybean fields nearby. So the drone will start from the bottom, that's near the soybean field, and then fly and towards the base station. So then turn towards, you see the little white house on the right, that's the LIBRAC, that's one of our animal science research farm. So that's where we have our own user equipment set up there as well to enable connectivity to that particular animal science research facility. Okay, so then drone will turn back and to the original location. So that's basically as a little triangle. That's how drone will fly, and so that's basically the setup. So I will ask Owen to show the interface and explain how it works. All right, thank you.
All right, let's see some drones fly. So right now, a couple of our team members are out in the field, getting ready to hopefully take off soon. And let's see if I can't put this down. There we go. Okay, so this is just a small interface for demonstration purposes. So in the top left, we can see the live video stream, which will be live. There we are. The bottom left is the map for your reference. The green home symbol is where they're going to be taking off from. The leftmost yellow star is that base station that we're going to be communicating with as that first wireless link. The second wireless link, which we use wireless backhaul, that Aviat backhaul to get to, is on that right side. And then the blue marker is LIBRAC, another UE, which we're just going to take a look at as part of our flight plan. On the right, we can see here some latency metrics. And you'll see 3 different lines to that first base station, to our edge server through the Aviat backhaul, and then finally to YouTube, courtesy of Hughes. On the bottom, we can get a couple signal statistics for that first Ericsson 5G Quectel link. So throughout the flight, we'll just get to see a bit of what happens as you get higher in the air or past the corn, etc. So at this point, I think we'll ask Alex to take off if he's able to hear us. And it is important to note this is the first step for this UE. We hope in the future to maybe do a little teleoperation, but as you might suspect, that involves reducing latency, which will be another step upon this drone UE's journey, is making sure that we have minimal latency with the streaming software so that it's feasible to do teleoperation from, for example, here, if I wanted to fly from here. Timor, I assume you're able to hear us and they're ready to go? All right.
Yeah.
What we've learned is with these very large drones, I assume Chris is here somewhere. Chris, as we know, the small drones are much easier to get up and going very quickly, but these large drones can take a minute to get in the air. Yep, should be ready to go. Let's see, make sure Alex isn't trying to. All right, and here's where you'll notice that okay, here we go. So you might notice some artifacting. Again, we mentioned driving down latency will be another next step, but another one is making use of liquid tunneling. I don't know if Evan's here, but if you get a chance to talk to Evan from our team, ask him about liquid tunneling and the way we can reduce jitter, reduce, for example, these artifacts that you might see. It's great for things like video streaming, maybe if you're doing some sort of gaming over the network. So here we are moving towards our base station. You'll see to the left of the screen, yep, now he's pointing towards Agronomy Farm Research, which we will see later this afternoon. And as we get closer, hopefully the base station will come into view. If not, you'll get a much better view later when we're out in the heat and humidity.
That's what we see the DEM, right? So SRP, so it's with line of sight, so it's much better. So for the base station, you see the blue curve and then
You know, if I had to make a guess, I'd be careful because I'm not great with distances. I'd say, I think we initially planned for 50 feet. I don't know. It maybe looks like he's a little lower than that. Another thing I'll note is down the road for this drone UE is adding a higher quality camera. So right now we're using an IP security camera. And if anybody has ever used an IP security camera or seen like the videos on YouTube, we know they're not the best quality per se. But the integration was great, and it seems to be doing the job right now.
So when is this one going through the tunnel?
Currently, it's not going through the tunnel, hence why you might see some artifacting. And down the road, we hope to integrate that liquid tunnel. And you might even see at Farm Progress show the liquid tunnel in use for a gaming purpose that Evan's going to show off.
Yeah, the other day when we did a dry run, we saw very interesting latency behavior. Essentially, without a line of sight, kind of a latency, different hops all going crazy. So you don't even know what to look at. But as soon as I fly above the corn line, the line of sight, so it's a beautiful, almost like 1 millisecond. But that's what we have today. It looks like so all beautiful latency requirements. So that latency actually for both the AraRAN part, we talk about your radio access network to the base station, also through the long distance 6-mile wireless backhaul. So altogether still is only like a 1 millisecond. So it's a very minimum latency. And so high latency, that's because we are using the satellite communication link. So that's what latency look like. There's some kind of variation there too. So that's basically those kind of setup can allow us to do many different types of research, right? So essentially different combination of all this different technology for different applications, different needs. So therefore, there's many possible setup, and so it's many parameters or behaviors we can optimize. So that's a lot of interesting things we can do.
So Alex is hopefully heading towards Liebrecht. You might be able to see it just barely, that white building in the distance that he's creeping towards. So we have another UE equipment located there.
Mm-hmm. Yes.
And I will say that the other day, and this is part of the fun of the drone UEs, the different things you can notice as you fly. So when we started flying that other day, we were right next to trucks, for example, right next to the vehicles that we had taken out to the farm. And you would notice, I think Going mentioned the reflections, for example, and you would see that play into the jitter and the latency. But as soon as you cleared the corn, like Dodgy says, you notice the latency smooth out, for example. So that's one of the benefits of not just a XY plane mobile UE, but a vertically mobile UE, is being able to catch things like that and test out those things and test out line of sight where you might not be able to without a drone.
See, he's going to hover and turn back towards the starting point now.
Yeah, so it depends on the payload, and what you'll see with drones is the manufacturer will estimate the duration that you can fly based on how heavy your payload is. So what we've noticed with this payload is generally around a half hour or so, but we try to err on less of that because there's a lot of expensive equipment that we don't want to crash.
Yes.
Operate together, okay, in this similar area, then how that will affect the performance of the latency and jitter?
You know, we actually haven't, but it is a wonderful idea to have, you know, multiple streams going, for example, where they are competing for resources, even in the same area. I think that'd definitely be another way or another place that we could take it and find out is how does that affect it when you have multiple UEs flying in the air, taking up bandwidth, doing a sort of stream like this.
Right, we don't have multiple drones, but we do have multiple UEs, more than 10 actually, different locations, some inside a plant, some in the field actually, so where a drone flew over. So that's basically some kind of resource management, so that's kind of interesting things to look at too, yeah.
And I guess now you can probably see where they are flying it from. I don't know if they'll give us a wave, if we'll be that lucky.
Yeah, probably you can have a peek of the Amiga robot too. That's our next, well, the third demo you're going to see. That's from the same field. Okay.
All right. Good.
We can switch back to the slides.
Okay.
Good landing, I guess. Where's the... How do I do? Thank you.
I think you can drag it down to the
This
bottom,
one?
right? Just
Where
drag
is
the
it?
whole window down.
This one?
Yeah, down to the right side is kind of where the screen's at.
Okay. Cool.
Is that it for that?
I guess.
Are we going to move to Amiga next? Is that the plan?
I mean, no, I cannot find a window. I don't know where that is.
You know, Ranveer joined us earlier. We actually working with Ranveer's
Yeah.
team trying some of the
Where is
data
it?
analytics. The
Okay.
slide is not
Yeah,
here.
okay. I don't
Okay,
know.
we
where
actually did something. We tried phone wipes for weak
Oh, this one.
detection.
This one,
is
right?
it not?
Can we show it again quickly, Roger?
Yeah. Just present. Yeah. Yes.
Yeah, so this is basically, we already talked about the many possible different research topics and for different wireless links. And so the bottom related to edge server, so I listed many possible interesting research like AI-enabled agri-rural innovations and also the kind of weather-triggered experiment and so on and so forth, right? So one of the applications we ran that's basically a Project Farm Vibes application by Microsoft. And so the goal, again, the project is to leverage AI and data analytics for precision agriculture. So that's so the top left figure, so that's essentially the picture we took from an egg farm near the green bean area over there. So you see some crop there, so then a bunch of weed on the side of the field, right? So that's basically we ran their weed detection application. So then depending on the model, so they will produce many different possible results. So that's where probably domain knowledge needs to be part of it. So essentially what you can see at the bottom, so the using that particular model that actually Farm Vibes did a pretty good job in detecting all the weeds and so on. So that's essentially an example of a precise weed control, right? As part of the precision agriculture. So obviously, I mean, we can do precise, say, irrigation management, which is, I guess, very important for today, so hot, and so also like a precise insect management and so on. I believe that's something Showmaker will talk about in the third demo, essentially to show that how the ground robot, and you can look at it like a different different part of the field and a different insect or bug condition and how to do better management for the entire field condition. Okay, so that's just some quick slide there to share with you. So this is there, but we haven't integrated that into the live demo yet. All right, thank you. All right, thank you. So Hong, you can continue with the second demo.
Sounds good. All right, thanks, Dutch. Owen, nice job. Sorry, can someone help me where to find the file?
Or second demo, right?
Yeah, second demo. So while we try to get the file up, this is one example. Together with last year's demo, this is one example how what you can do with the commercial grade 5G platform with a focus on application, right? We kind of, one of the future work would be actually, assuming we can stream this data back, right? What kind of ag research we can actually use this, to run experiments. So next we're going to look at an experiment of different flavor. This is going to be looking to the 5G internals in many ways. So we talk about open source 5G platform support. So this is a kind of experiment, give you just an idea, the kind of work you can do in Era using the testbed. So the focus is going to be on, so present, just click here. Oh, there are two, one, just click here, one of them.
First one, right?
No, okay. Which one is this? Let's just,
Yeah, it has the graph.
it has a graph, right, okay. Right, so this is one example where we're going to show, something's wrong.
Yeah, this cursor doesn't work.
Huh?
Cursor doesn't work actually.
Just this one? Oh, the laptop. Huh? It's not moving. Did you open two? Just maybe just close this one.
No, that was the same.
It was the same.
Yeah. So basically, yeah.
Okay,
You can start.
this one.
So if you change the slide, it will change it.
Okay, it works. Right. So here we hope to show one example of how we can use the open source platforms to try out experiment with a focus on actual real-time communication. As we know, there have been a lot of use cases of real-time, highly reliable communications in agriculture, other domains such as transportation, manufacturing, and so on. And of course, we all know that for folks in the wireless communication systems domain, ultra reliable low latency communication has been one of the focus area for 5G, but the real world adoption use has been limited, right? There are actually many reasons for that. Some of those are actually technical. So I thought, just for folks who have not looked into this space, just to give you a little bit of background about something that has been operational in practice. That's not wireless, but wireline industrial networks. This is one of them, the Profinet. In particular, the asynchronous real-time communication systems in Profinet. My intention here is to give you a flavor of how the traditional mission-critical wireless wireline systems was developed, right? So that the IRT for Profinet was designed for motion control to guarantee, for example, provide precision guarantee of about 1 microsecond up to 100 nodes, and then be able to support an update rate of 1 packet every 1 millisecond. So this is how it's designed. In this example, you have it's a centralized TDMA solution, basically. You have a controller that's deciding how messages get delivered to the individual devices in the time division multiplex fashion. What you can see here is basically from left, sorry, I couldn't, if you can watch the left-hand side, right? Basically, the message, you get 3 nodes, then you have 3 messages get embedded into one packet that get transferred, get delivered into one node, and then get one, for example, when device get it, one get it, it's going to strip off this one and then forward the 2 other messages, and then the third message to the third node. Right? It's a very structured, right? Very structured TDMA solution. In addition, even if this looks simple, they have to implement this TDMA scheduling in hardware, in ASIC, right? So to enable precision timing control. But of course, wireless is quite different, right? In wireless systems, a lot of uncertainties are dynamics that cannot be controlled. It's difficult to have such a structured approach. For example, there's actually channel dynamics, interference that's there, also mobility and other even potential malicious attacks, right? So here in today's short demo, we're going to give just focus on the first 2 parts, the channel. Some of the work we're leading in how to address channel dynamics and interference. Just to give you a focus for new to this field, this is a kind of a time series data showing the signal to noise ratio for the typical NIC in era today, right? So as you can see, the variations are actually quite big. The SNR varies over about 10 dB. That's actually a huge difference, right, in terms of communication quality that can be that can be enabled. So then the broad question is, in such highly dynamic, uncertain wireless networks, how can we potentially bring in some sort of structure and predictability despite the dynamics and uncertainties? So that has been a question that I guess in our research group and also more broadly in the real-time systems community have been looked at. The specific question we hope to kind of share some result today would be about the question of how can we even potentially enable poor packet reliability guarantee in such highly dynamic uncertain networks. Now, to answer this question, essentially, ultimately, what's impacting the reliability to a great extent is actually the SINR, signal to noise, interference plus noise ratio, which basically says if your signal is strong enough compared to noise, then you can actually have the signal delivered. Just as if I speak louder enough, much higher than the background noise, you can hear me better, right? So now, to guarantee poor packet reliability boils down to guarantee the poor packet signal to interference plus noise ratio. Now, to that end, basically there are 2 important parameters we want to control. One is the receiver side interference, the I, right? So if we can control the distribution of the I, then that gives you a foundation to control the SINR distribution, right? So there are actually techniques of doing that. One reason, there's actually discussion about interference earlier. This is actually remains a challenging problem, right? So because in large-scale networks, interference is highly non-local. How can you enable predictable control of receiver-side distribution in a predictable way, right? So there are actually some approaches that have been studied, looks very promising, that you can, folks interested, you can check out. But assuming that you can do that, then the next step would be to control the transmission power. Assuming you know the receiver side distribution of noise plus interference, and then you want to say, now what transmission power should I choose to guarantee the distribution of SINR, then you can actually pick a transmission power depending on that objective. So this is going to be our first mini demo today that Zibo and Elizabeth are going to show us shortly, showing how you can use error testbed to try out such transmission power control techniques. The other part, now the moment you can guarantee the poor packet reliability, then you can ask the second question, which is, now if I can guarantee the reliability of each packet, then can I guarantee in a probabilistic fashion the delay of each packet transmission? Turns out the answer is also yes. Conceptually, it's something like this. This is a model for probabilistic real-time guarantee requirement for application that could be seen. I'm going to generate packet every TI seconds. And then for each packet generated, need to be delivered by this deadline DI. And then I want this guarantee to be the probability of ensuring this guarantee is no less than capital P of I. And also under the assumption that the per packet reliability is small pi, right? Under this assumption, you can actually transform the problem into something that's more or less like a deterministic real-time scheduling problem where you can essentially transform this probabilistic guarantee into the number of transmission opportunities we want to give to each transmission. And then I know, sorry if this is a little bit too deep in the weeds, but essentially with this transformation, you can actually leverage some other features we have found in terms of interference control, like local interference relation. Essentially, you transform the scheduling problem becomes a shared resource allocation problem, actually in a localized fashion. And then you can actually leverage a lot of existing theory that has been there from the past decades to study the problem. So that's what we are going to show here, just kind of 2 example problems, how you can control the transmission power using and try it out in the field, and then how you can do the scheduling. So with that, let me actually then, Zibo, do you want to come up? So Zibo is going to share with us the setup. The piece background, I think this is open source, right? Open source platform out in the field. So we'll see how the live demo goes. But we do have some recording in case, because we did notice actually some external interference just happening in these few days. We still need to figure out. That's actually impacting the live. Yeah.
So hi everyone. So I'm Zhibo, and I'm a PhD student in the YSI Center, and I will lead this demo. So firstly, this is our whole system and software architecture. Where's the mouse? Okay. And so from my side, I mainly focus on the OAI and some core network part, basically the run part. So we deploy our OAI base station in the field, and also deploy the OAI UE in some field node. And the SD core, we also deploy the SD core at our Era data center. So basically in the OAI base station, we employed our own algorithm, the power control and the real-time scheduler in the base station. And so the base station will get some input from the UE, and then the base station just do the algorithm and generate some output, and using the downlink control channel to transmit some downlink the control information to the UE. And once the UE get that control information, and to just do the action locally. And for the web server, maybe Zebras, you can explain a little bit.
So in this demo, we will see a web server where user can input multiple commands, for example, start OAI, or configure some parameter for our configuration for specific to our algorithm. So for that, user will have an interactive UI, and for sending the command, we have installed multiple backend server at each compute node and the UE, base station, and also core network. In this setup, the backend server will enact or activate every command we send from the UI or UX. However, to be noted that this is still a beta version of this overall system. So in case there is any disconnection, I probably have to do anything locally from my SSH terminal. So I hope you guys enjoyed this demo. There will be 2 main segments. The first one, we are going to show SNR tracking measurement, where we can see the SNR changing, and then the second part will be latency tracking.
Okay, so firstly, we will show our first demo. That's for the power control for predictable SNR tracking. And this is our map showing the deployed base station and the UE. So basically, we are using the, this is the Wilson Hall base station and the Ames UE. So we will connect this link together. And this is the Curtis Farm base station. This is another UE around the Curtis Farm. Okay, so firstly, so this is our GUI, and here is the map, and we can, okay. So I'm going to connect these two nodes together. So this is base station and this is UE, and I will start it. So the current GUI is a beta test, so we just show some function of it. And right now I'm waiting for these two nodes connect each other. Okay. Okay, we can see some data coming from here. That's the SNR for this link. That means they already connected each other. And so right now I'm going to do the iPerf. So currently without any power control. Okay, I think it's enabled, and there's a little delay between the app and the backend server. Okay, currently this is without any power control, and we can see some SNR drop very quickly here. That may be because the external interference or the environmental factors. So right now I'm going to enable it. So firstly, I will pick a lower number, which is 15. Okay, I think it works. So this is 15, and we can see the SNR can be guaranteed above 15. And then we'll keep increasing this value. Yes, there's a delay between the app and the backend server. Actually, yeah. Yeah, currently the SNR can be guaranteed within 70. I think it's 0.9 maybe. Yeah, sometimes we can see some fluctuation. So one thing maybe because this app, there are still a bug for the displaying the data. And another issue is the external interference. We can see some drop down very quickly, the SNR. That is the external interference. It's not caused by the OAI. And then we'll input another value. Okay, we can see the SNR increase, and actually it can be handled above the 19 threshold. And for this link, when we do the test, I think the SNR 19 SNR already achieved the maximum transmission power for this UE. And then I will stop it and show the impact of the SNR to some network metrics, such as the throughput, jitter, and the reliability. So currently, this is the same base station, and this is the MCUE. This is the SD core in the data center, and so currently I'm connected the Wilson Hall and the UE. Yeah, and right now I didn't enable the power control, and then I will enable it. So the first value is 14. And then I will enable it in the UE side. Okay. Okay, we can see this is the per packet SNR. Actually, for this demo, for this video, the SNR can be guaranteed very well. And we can see the throughput. This is jitter. This is the packet loss. And then I will increase it to maybe 16. And we can see a difference between in terms of throughput, jitter, and the packet loss. And then I will keep increasing the SNR. So right now it's 18. Yeah, we can see the SNR tracking is very well, and also some improvement for the network matrix. So finally, I will increase it to 20. Yeah, we see some improvement here. And then I will show the impact of the interference. So in this video, I enable two links. So the left is the Curtis Farm, and this is Curtis Farm UE. This is Wilson Hall, this is MCUE. So this is one link, this is another link. Okay, so currently they transmitted together, and we can see the SNR fluctuated very much. And then I will enable the power control to control the SNR to be stable. Yeah, first the threshold is 15 for both links. Yeah, I think they already converge, and the SNR can be above 15 dB. And then I just increase the SNR threshold a little bit. Yeah, right now the threshold is 16. And I think finally we can increase it to about 19. Oh, I think 18 may be the final threshold. So that's it for the interference. And and then I'm going to show another demo. So this is the second demo. That's to show the real-time scheduling. We use the ergonomic farm base station and the two UEs around the ergonomic farm, which is UE010 and the UE001. And okay. Yeah. So this is the left up terminal is the base station, and the lower two terminals are the UEs, and this is our core network. So I'm waiting for the two links connect to each other. Yeah, currently two UEs connect to each other. We can see two RNTIs here in the Geno B terminal. And then I will transmit our real-time traffic. Okay, in here, so this is the data when we enable the real-time scheduler, and we measure the one-way latency in the run side. So that means this latency is only in the run and without engaging the core network. Yeah, we can say the one-way latency is around maybe 6 to 7 milliseconds. And we didn't show the per packet latency here because that will update too much. And instead, we take 50 packets data and do the average for that 50 packets. And then in here, I disabled our real-time traffic, disable our real-time scheduler. We can say increase in terms of the one-way latency. That will increase to around 10 or 9. And we can also see increase of the jitter for the one-way latency. Okay, I think that's all for this demo.
Right, so this is really just a proof of concept, kind of what you can do with open source. You can do some deep dive into the layer, do latency measurement. So the last demo is going to be led by Sumik. He shared earlier about his work. So this is going to be a feature of one of the robot, maybe Daji.
Hello. Okay, I'm supposed to be here to introduce Shumik, but no no introduction. So what Shumik is leading like 2 centers. One is both are AI related. What his centers are doing are perfect sort of complement with what we do, and so it will provide enabling technology. So altogether we can have precision agriculture better, bigger, faster, and so on. So that's basically how this is a perfect sort of combination here, right? So show me.
Thanks. Yeah. Awesome. Thanks. That's okay. Yeah. That's okay. All right. So again, so I kind of briefly talked about what some of the projects that we are working on do. So in the interest of time, I'll just quickly run through some of the big picture objectives that we have as it comes to using wireless communications in the field setting and ARA in particular. So as I said, that we are looking at several cyber ag systems problems that require wireless connectivity. So some of the things that you're going to see today, it's basically part of our projects where we are doing robotic pest monitoring. And the idea is that these robots we have equipped with cameras, and it has a sort of Jetson Nano or some type of processor that it can actually process something on board. And also it can, like some of the specialized robots has sprayer built into it that can actually spray, if there is a, if some threshold it goes beyond some threshold, if it, identifies more pests or insects or weeds or whatever. In particular, we were interested in, can you, of course, the easiest thing would be, can you just, pass metadata from the robot to the server, and essentially that sort of brain where you're making a lot of decisions, which robot goes where, what action they need to take, and so on. But then we were also interested in, can we be a little more greedy and actually send raw data, so images, videos, and other things. And that is specifically for a couple other examples. So one is a remote breeding trial. So we have these sort of large 360-degree video cameras that are mounted on robots that goes around and that can take a full 3D view of the field, where basically an agronomist or a breeder can walk through those fields virtually. So with AR and VR setup, they can essentially, as if they are walking with the robot. So that's kind of our sort of dream application, where you could real-time, extremely high bandwidth communication can we have. And then finally, sort of building and maintaining agricultural digital twins is kind of going one step from that. That as you are collecting this large sort of 3D data, can you also sort of keep building and maintaining digital twin models that has detailed geometric and biophysical information of these plants, right? So bottom line is we have multi-sensor, multi-platform sensing and actuation, but there are heterogeneous requirements in terms of bandwidth and latency. Different applications have different requirements. So roughly what we have for you today is we have that robot Amiga. It's a general multi-purpose robotic platform. You could basically retrofit it with many different ways. So in this particular one, it basically has some cameras and some processors, but we also retrofit robotic arms for precise manipulation of plants. So we essentially put nitrogen sensor in plants with robots. And also you could add sprayers and other things that I was talking about. So these robots are kind of talking through the ARA tower. And essentially, the goal is a lot of our MLOps and data data management is running as part of the Cybers team in Arizona. So this needs to go out of the firewall and be open to the internet, that the Arizona team can actually collect and store and manage and run MLOps if necessary, and so on. So roughly this is kind of again very toy setting here. These are called the sticky traps. So these are yellow sticky traps where insects get stuck on. And the current practice is a farmer needs to go and walk through and scout his or her field to essentially monitor that how these what kind of insects are getting stuck in there, and how many of them. So kind of detecting, counting, classifying, and based on that they make decisions whether to spray or not to spray, or when to spray, where to spray, and so on, right? So now we are trying to make all those scouting remote and automated, because in many cases with the large fields that folks have, they are not able to scout everything, and in a matter of 2-3 days we have seen on a big part of the field wiped out by certain insects and pests. That can happen actually. So it's a pretty time critical thing as well. So this is kind of a more zoomed in. So that's the Amiga robotic platform, and we have a UV box that is on the robot that it's talking through, and this is kind of what you see, the camera and the sticky trap. So just this is my last slide. So this is kind of our cyber infrastructure, where the data that is coming in and that is going through we call it the EDI platform. Essentially, it's a event-driven detector. So the idea is that we have in the MLOps side we have models, and our machine learning people are updating those models, and those models need to get updated on the IoT side, so on the robots. So these robots can completely automated way call and fetch new models if they're and then send back the data, the raw data as well as the metadata that it's collecting, and things we sort of set it up with something called a things board interface where we could set rules. So farmer can go in and set rules that, okay, if I see in matter of a week, these sticky traps go above 20 insects of this type, you need to spray. So you can set up those rules, and the vision is these robots will automatically execute that. So it's a lot of back and forth communication, both of raw data and large machine learning models that we are shipping to these robots, as well as actuation signals. So that's what I had. I don't know, Avan, and whether you folks are ready to go. All right.
We are ready to go.
Oh.
Thank you, Shomek. All right. So at this point, we will show you again the folks out in the field sweating for us.
Here we go.
Yeah, more or less. Okay. So what you're seeing right now is footage from the Amiga robot. So Shomek's team has mounted 3 cameras on the robot at this point. So the top left you will see is a a forward-facing camera that's pointing ahead of the robot. Truly, all the action for this demo is happening to the right of the robot, and that's what you see on the big window. The bottom left is to the left. Again, not much interesting happening there, but if you want to look at corn, you're more than welcome to. So in a minute, I'm going to have the team go ahead and start moving the robot forward, and you can see what they would see in real time as they're processing the data. And here we go. So they're going to go ahead and move the Amiga forward, and eventually we will stumble upon a yellow sticky trap. So this is the point at which you can use an edge processing model to make decisions based off of how many insects are on the trap. Do I need to do something? Do I need to actuate something in this field to handle that problem? Or maybe you're just collecting data to know that you have, I believe, Japanese beetles eating all the soybeans in this field. You actually will see tons of holes in these leaves, which is a result of them. And as you go out there later today, hopefully we are not swarmed by bugs, but if we are, you can think of this Amiga demo and think maybe that will help solve the problem. Uh-oh, looks like... a moth or butterfly. Yeah. Which is not the target for these pheromone traps, but I suppose they will stick to anything.
The ultimate vision is to have everything teleoperated, right? So Joseph doesn't have to be there. So we
Yep.
can all just sit in the room comfortably, and a robot will do their job. So that's an excellent example of how we can all work together to make this a precision agriculture reality. So that's what this demo is about. So now the robot is kind of back into the location, right?
Yep. That is, I think, all we have to show for this demo right now until we go see the Amiga in the field later.
Thank you. I think that's all we have as 3 demos for you. Hope you enjoy watching and listening to the presentation. So, Hong, you can say how we can go for the field trip.
Yeah, sounds good. Actually, that's a soybean. It looks a lot nicer on the screen than in the field. Okay, so I think we are heading out right now. John where's John? We should have shuttle. We should have.